the recording. Okay. Before we start today's lecture, I would like to make an announcement. Okay. The summer one will be released after the new Chinese New Year holiday. Okay. I'll repeat. The summer one will be released right after the Chinese New Year holiday. Okay. I believe that we can finish enough material that we can release the summer one after Chinese New Year holiday. Okay. I believe that we are able to finish the discussion on some algorithms right before the week of the Chinese New Year holiday, and I want to let every one of you enjoy your Chinese New Year holiday. So I will release the summer right after the Chinese New Year holiday. Okay. Okay. So any questions? So regarding the assignment one, it will be a written assignment. Okay, it will be written assignment. You will need to do some dry run of some algorithms, okay, and give me the results. Okay, and some MC question as well. Okay. If you are interested to kind of know what assignment one look like, then you can actually check out the past paper of this course. Okay, the assignment will have a similar style to the examinations. Okay. Okay. So any questions? So any questions about the assignment arrangement? Any questions? Any questions? Then now let's go into the discussion of the lectures. Okay. So in the previous lectures, I'm opening up the slides. I don't like that. So I believe that in the previous lecture, we can actually go through the tree search algorithm. Okay, we actually go through the tree search algorithm. Okay, and one thing you must remember is that when we are trying to solve problems using the approach we discussed in lecture 3, it is substantially different from what you have been doing. Okay, maybe you think that I'm a little bit annoying repeating the concept a lot of the time, but I will need to make one more reminder. Okay, so the approach we talk about in lecture 3 is actually quite different from how you solve problem in the past. In the past, when you are given a program problem you will need to solve, your approach is that I study the input and the output of the problem, and I would need to create my own algorithms, create a list of instructions, okay, that can solve the problem. Okay, and I then need to implement my algorithm, my software design into coding. Okay, so this is what you have been doing in the programming course or in other courses related to programming in the past. Okay, okay, but if you take a look on the sample code I released for lecture 3, you'll find that when I am defining an object for representing the travel problem, okay, the coding part of the travel problem only contains data. It doesn't contain any code for computing and solving the problems. Okay? Okay? All the actual coding we use for solving the problem is actually done right here. And although I haven't covered what is background search, but if you use your coding knowledge and study the code, you will find that all the coding I listed in this function are not related to the travel problem at all. Maybe 1 to 2 sentences, maybe 1 to 2 statements, I defined the initial state and the goal state, and then created the object for solving problem, and then that's it. You take a look on all the coding, okay? on all the coding. Sorry. Sorry about that. Wait. You take a look on all the coding that is shown here for the search algorithm. You can find that all the verbals here, all the terminology here are not related, okay, to the truffle problem we are solving in the first place. We have isolated the algorithm solving part from the problem definition part. Okay? Any one of you actually download the code and actually run it at home on yourself? Anyone? Really try it, okay? Or the code really works, okay? I write it and I debug it and I run it, okay? It is something that you can really run, okay? And this is the beauty of this approach, okay? You can actually consider all the coding that I write for the truffle problem, okay? This section of the code is merely defining the problem for the computer to solve, okay? The actual algorithm for solving this problem, I don't implement it, okay? I am merely just converting the definition that I have into a data structure that the computer can understand and can utilize when the algorithm is being executed. Okay? So you can actually consider these approaches. I tell the computer the problem and the computer solve it for me automatically. Okay? So many students think that this is not AI, but if you take this approach, okay, you consider this approach as I have a problem and I rewrite it into a form that the computer can understand, and the computer run the defined algorithm to solve the problem. If you take this perspective, then it is a AI, because we humans doesn't need to redesign or we construct an algorithm from scratch when we are solving the problem. All the problems, if you are able to convert into this form, then the rest is solved by the same solver, by the same solving algorithm in your computer. Okay, so it is similar conceptually to using modern day AI in that is that you do not design the algorithm from scratch and you let the predefined algorithms in the computer to solve the problem for you. Okay? But the differences between this approach and ChatGPT is that now the computers in the 1970s and 1980s is not sophisticated enough to directly work with the natural language that you have for your problem. So you need to manually convert the natural language definition of the problem into a rigid definition such that the computer can handle the rest. Okay? But nowadays, ChatGPT is able to read your natural language problem definition and solve the problem on its own. So that is the main difference here, okay? But the general conceptual idea is still the same. You have a problem, you don't need to figure out an algorithm to solve it. You just convert into a format that the computer can understand and let the computer handle the rest. Okay? So in the conceptual idea is that you never need to create an algorithm by yourself. Okay? You just convert your problem into a thing that the computer can understand and the computer solve it for you. So that is why we consider it as AI. Okay? Although it is the most primitive version of the AI. Okay? I understand that it is a little bit difficult for you to accept this is AI, but let's remember all these algorithms are invented in the 1970s and 1980s. Okay, the computer at that time, this is the best it can do. Okay. So any questions? But you may ask is, Professor, why we still need to learn this way of solving problem? The reason is that if you are going to work in the computer games in the future, this approach is still widely used for porting, okay, for porting a route for the character in the game to move through the terrain or move through the stage, okay? Okay. So in the game, in a game, okay, the character can move around, okay? We call this background that the character can move around as the terrain, okay? And terrain is not, it will have some object that block the character to move around freely, okay? So if you want to order the character to move from one place to other, then you will need to find a path for the character to do so. And for solving this kind of problem, this approach is still the best approach. Okay? 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 So this is the reason why you still need to learn this kind of algorithm. Because in certain applications, this is still the best approach when compared with other algorithms that have a heavy computing cost. Okay, such as ChatGPT. Okay, so any questions? So any questions? Any questions? Any questions? Any questions? So last time we actually also go over the tree search algorithm, okay? Although it seems the tree search algorithm is very primitive, okay? Essentially, it works in this principle, okay? Each time we start off with the initial state, and then we start off in the initial state, and then we check what is its neighbor, okay? And for its neighbor, we keep track into our computer, okay? And after we discover the three neighbors of the initial state, we keep on taking the neighboring state of the initial state to search for other neighboring states. Okay, so we gradually expand our exploration in the search tree, in the state diagram. Okay, essentially we are trying to generate all the possible paths starting from the initial state. Okay, if we're able to generate all the possible paths starting from the initial state, and one of the paths actually is actually reaching the goal state, then we can find a path starting from the initial state to the goal state. So this is how intuitive this algorithm is. Okay? Okay? The layman term or the overall observation of this tree search algorithm is that I actually keep on exploring the search space, okay? And in the process, I generate all the possible paths that start from the initial state. Okay? If one of the paths actually hit the goal state, then I would actually say that I reached the goal state. I find a path starting from the initial state to the goal state. Okay. Yes, okay, you may find that this approach is extremely simple, okay? Just enumerating all the possible pathway, but that is the reality, okay? Okay. Essentially, the tree search algorithm is enumerating all the possible pathways, okay, that start from the initial state, okay, and it keeps on generating until we stumble upon until we reach the goal, until we find a path that reach the goal state, then we stop. Okay, okay. So this is the core idea of the tree search algorithm. That is to gradually generate all the possible paths starting from initial state. Whenever a path generated reaches the goal state, then we stop. Okay? Okay? But if we are taking a look on this algorithm we need to solve two problems. The first problem is how we record down the search process up to now. We need to have a data structure that stores what kinds of path we have been exploring up to now. Okay, so this is the first problem we want to solve. And we can solve it by using the search tree. So you can see that in the search tree, we start off with an initial state. And for all the neighboring states that the initial state can reach to, we add it at the end, or we add them as the child of the initial state. Okay, so we start off with the ACT, that is the array. Okay, and then from array, the agent can actually move to Cebu, to Cirrus, to Timisoara. Okay, so these three nodes are being added as the child of the array city. Okay, we use the child and the parent relationship as the representation of which start first and which they start first and which they start later. Okay, okay. The parent and the child relationship in the tree is used to represent which state is the successor of another state. Okay, okay, okay. So from this search tree, we can know that the array, okay, is being the initial state, and it can travel to Cebu, to Cirrus, to Timisoara. Okay, and the parent-child loop relationship is representing the ordering of the states. Okay, okay. Then the agent can go to Cebu, can go to Cirrus, can go to Timisoara, right? So for each state here, we can do further exploration. Okay, and when we do further exploration, we add into the search tree. So we keep on adding log to the search tree. Okay, and we keep on going the search tree, and whenever we reach a point that the goal state is being added to the search tree, we can call it the end. Okay, okay. So you can see that we are using the search tree as a data structure to keep track of what we have been explored so far. Okay, you can consider it just as when I'm doing the exams, I have a draft paper, can keep track my calculation process. Okay, the search tree is acting in our main memory to keep track what nodes we have been explored so far. Or I would say what path we have been exploring so far. So if you take a look on this search tree, the array to Cebu to Fagurus, okay, you can see in the diagram that array can go to Cebu and then go to Fagurus. Okay, this path is represented as the array to Cebu to Fagurus. This line in the search tree. Okay, this branch in the search tree. Okay, if you take a look on the search tree, you will find that the node array is pointing to Cebu and Cebu is pointing to Fagurus. Okay, this hierarchical relationship is actually representing the real path in the search tree from array to Cebu to Fagurus. Okay, so you can consider the search tree is recording all the possible pathway we explored so far. Okay, so any questions? So any questions? Any questions? Any questions? And inherently, because a node in the search space have more than one neighbor. Okay, for example, in the array here, is the initial state have 3 neighboring nodes in the search space. Okay, so naturally, the search tree is not a binary tree. Unlike the binary tree you have learned in the data structure course. Okay, okay, and you can consider the depth layer of the search tree as the ordering of the node that is appearing in the path. Okay, for example, the node with the depth 1 is actually the first node that appear right after the initial state in the pathway that can be generated. Okay? Okay? So the depth of the search tree is actually also indicating the length of the problem of the solution of the problem you are solving. Okay? You can also consider the depth of the search tree of a node of a search tree is representing the length of the solution. Okay? 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 So any questions? Any questions? Any questions? Any questions? Okay. And the next question that we would need to handle, okay, is what nodes we need to explore first. Okay. So as you can see in the search tree, okay, the series, okay, is still not being explored. Okay. Where agent is a series, that it has other chances, other possible pathway we can go to, but we never explore first. But we never explore that. Okay. On the other hand, we have regulars, ODS, and TV and remedial VCHAR under the CFO. Okay. So for regulars, for ODS or for remedial VCHAR, okay, whether we should explore these three nodes first. Okay. So if you take a look on this diagram, you can see that the regulars, the ODS, the remedial VCHAR being the deeper node in the search tree. Okay. And the series and the TV solar being the shadow node in the search tree. So what is the ordering of the node that should be picked for exploration? The choices would actually contribute to two different algorithms. The depth first search would prefer deeper nodes. Okay, so it will keep on exploring the node along a path until that path no longer reaches the goal state or already reaches the goal state. If such situation occurs, then it backtrack. Okay, so the depth first search will prefer the deeper node. So in this case, the depth first search will actually work on the factors, the ODS and remedial VCHAR. Okay, but there is another search algorithm called the best first search. Okay, for the best first search, okay, it will prefer the shadow node. So after exploring SIBO, so it will go to explore series and TiMi Sora, okay, the shadow nodes, before it explore the deeper nodes. Okay, okay. And you can also, and because we have been talking about the fact that the search tree is representing a collection of the path starting from the initial state. So you can also choose the path that have the least cost for exploration. Okay, so that is called uniform cost search. Okay, okay. And all these algorithms, they are programmed in the same manner, but the major differences of these three algorithms is which node is prioritized for exploration. Okay? Okay. So in fact, we would actually have a component, we will actually have so-called the search strategy. Okay? The search strategy is determining what node should get selected for exploration first. Okay? And in fact, if you take a look on the implementation of the uniform cost search and the depth first search, okay, maybe I will try to wait. I will try to do this. Oh no, not this one. No, do this. Okay. So at the left hand side, I hope that this is more easy to understand. So let's talk about this using coding. Okay. So in the screen, you can see that at the left-hand side, we have the depth first search, and on the right-hand side, we have the breadth first search implementation. Okay, all the code can be really executed. Okay, and if you compare it side by side, you can actually find that the two algorithm is substantially the same. Okay, except one thing. The breadth first search is using a queue. Okay, the student at the back, can you see the code clearly, or do I need to enlarge it? Do I need to enlarge it? Okay, so if you take a look on the right hand side, the breadth first search is depending on the queue. But if you take a look on the left hand side, the depth first search is based on stack. Okay, so the so-called search strategy is actually implemented by using different data structure to keep track what nodes should get explored first and what nodes should get explored later. Okay, okay. So maybe you have been learning data structure like stack and queue, or I believe you have also learned priority queue, right? You have learned a thing called priority queue, right? You have learned priority queue, right? Okay. And don't worry, I will teach you what is priority queue later, okay? So if you recall what you learned in data structure, okay? So you must have at least learned stack and queue, right? You know what stack and queue, right? So you may think that stack and queue is just two data structure to keeping track of data. But in fact, in some algorithm, the properties of how the element in the stack and queue is being retrieved will already be enough to change the properties of the algorithm we are working on. Okay, so that is the beauty of data structure. Okay, when we are discussing the tree search algorithm, we talk about the strategy for choosing the node for exploration. It seems to be a technical jargon term, like the term you would listen to when you watch sci-fi movie, okay? But in fact, the so-called search strategy is when it comes to implementation side, it's just the choices of using stack or queue for storing the node for exploration. Okay, it is actually that simple. Okay, so this is the reason why you would need to spend a lot of time to learn data structure. Okay, the careful use of data structure will contribute to a good algorithm. Okay, search strategy to choose the best node. A lot of technical jargon words seems to be difficult to do, but at the end, it is just the choice of stack versus queue. Okay, so that is why you want to spend time learning data structure, because you want to master the data structure and to use the correct data structure to implement your algorithms, as you can see here. Okay, okay. Any questions? Any questions? Any questions? Any questions? Any questions? So, maybe you need some time to do some digestion, okay? But anyway, the code is always available in the Moodle. So if you are interested to study them, you can take a look at home, okay? You can even try to run it, modify it, to see for your better observation. Okay? Okay. So let's get back to the lecture notes, okay? So one thing we need to discuss is the search tree, okay? Because the tree we need to create a data structure to keep track on the path that we have been explored, okay? So we need to have a tree that looks like this, okay? So in this search tree, you can see that there are more than one node. There are more than one node, okay? As the child node of a parent node, okay? So for example, the Iraq city, okay, the root node of this tree have 3 children, okay? And the Cebu node have 4 children, okay? So clearly, the binary tree data structure you learn in the data structure course will not be actually applicable in this scenario, right? Because we need to have a data structure that allow our tree to have more than 2 nodes for each, more than 2 children nodes for each node. Okay, so binary tree doesn't work right here. Okay, so we need to reinvent a tree for us. Okay, and just to remind every one of you, okay, I understand that you are used to the idea of tree being a binary tree, okay? But in fact, in data science, binary tree is only one type of tree, okay? We can have other trees that can have more than one child node, okay, for a node, okay? So for example, the B plus tree can have more than 2 child nodes for each node, okay? And it has a data structure that is vastly different from the binary tree. As you observe the B plus tree, we can have more than one values in the node in the B plus tree, okay? And you may learn it in the future when you are taking database courses or if you are learning things like the file system in operating system, okay? The B plus tree is actually widely used in the file system and in database. Okay. If you are learning, if you have the chance to learn postgrad level courses, okay, some university will actually consider working with files, working with data stored in secondary storage as a so-called data structure with external data source, okay? And it is some university will consider it as a master course, okay? And you may in those courses you may learn a thing called B plus tree that is used in database and file system to keep track of record. You don't need to understand what is B plus tree, but if you take a look on the structure of the B plus tree, you can see that it can have more than one node, more than 2 child node for each node, okay, and a node can store more than one values, okay. So the binary tree that one node can only have 2 child and one node only can store one value is the design of the binary tree, but other trees can have other design. Okay, this is the takeaway message you must have. Okay, okay. So you may be used to binary tree looks like this. Each node one data, okay, and each node only have 2 child node. But in fact, if you other type of tree like B plus tree, okay, can have different design. Okay.
So, excuse me, just a quick question. Like, so in B plus tree, I see that there are like 2, boxes.
Yeah.
Yeah.
The operation of the B plus tree is actually out of the syllabus of this course, so I will not go into the details. But I'm just taking as an example to demonstrate that the binary tree is only a very oversimplified example of trees that you learn, okay, in the past.
Of course, usually in real life, we have, like 3 or more,
But binary tree, but the reason why I need to explain this is that many students who have taken data structure in the past, they may have the misunderstanding that there is only one type of tree that is called binary tree. Okay.
Okay.
So I'm trying to explain this concept. Okay. In reality, when you have different applications, then you have different kinds of trees. Okay. So this is not, you don't need to understand how B plus tree works. Okay. This is just an example. Okay. But you must learn what is search tree in this course. Okay. So this is what we want to include in the search tree, okay? So in the node here, we would want to store the action that will lead to that is done before the agent moves to this node, okay? And we also want to store the depth of the node, okay? And we also want to store the path cost of the node, okay? And of course, we want to store the child of the node, okay? So the reason why we want to store the action or that lead to the agent moving to this state is that at the end of the problem solving process, okay, we don't just want to have the sequence of states. We also want to have the sequence of action that lead to that sequence of states, okay? And solving the action right within the search tree allow us to reconstruct the final solution. Okay? Okay, so this is the reason why we store the action that lead to the agent going to a node into the nodes. Okay?
So is this stored in the child or the parent?
In the parent. Okay, so for example, if the node at the parent need to do an action right to go to the node we shown the diagram here, then the action right will be stored in node in diagram right here. Okay. So for example, maybe I will use this one as an example. Okay. So you can see that you can consider the action stored in node as the action that is done by the agent that lead the agent go to this state. For example, the Cebu node right here, okay, it is storing the action erect Cebu, okay, because the agent at erect need to take the action to go from erect to Cebu in order for the agent to reach to Cebu right now. So the action of each node is storing what action that lead to the agent get to the state we are talking about right now. Okay.
So is it stored in C?
So in the Cebu, yeah.
Oh.
So any questions? So and for the depth and the path cost, we store it because we want to keep track on how long the cost and how long our solution actually is. Okay. Okay. So if you take a look on the implementation, this is how we actually implement it. Okay. So maybe I will try to split the auto panning feature of the computer is very annoying. Okay. So I will try to do things like this. Okay. Okay. So as you can see here, wait. Okay. So as you can see here, now I've configured the screen such that the left-hand side is showing the graphical visualization of the tree structures, and the right-hand side is actually showing the structure of the search tree. Okay. Okay. So you can see right here that we, in order to at least form the search tree, you must at least store, okay, the following things, okay. You must store the parent node, okay. You must store the action, you must store the state, you must store the path cost, and you must store the path, okay. You can also choose to store the child node reference, but we have another data structure to keep track on what node is not being explored first, so that is not necessary. Okay. Okay. We have another dedicated data structure to store the node that is at the terminal side and haven't been explored. So as a result, we don't need to explicitly store the child in the search node. Okay, it still works. Okay, and if as you can see here, for the parent node, we assign none to it as the initial value, so we expect to put a object reference to it. The object reference will be pointing to a parent node of the search node we have, and the action is also an object. It depends on the problem you are trying to solve in the first place. Okay, but most likely it's just a string. Okay, and for the state, again, we need to store the state that the node is representing. Okay, because the search tree is actually representing a series of paths that we have been exploring so far. Okay, so at the end, you still need to, of course, store the state that is represented by the node. Okay, so that is why you have the state for the search node. Okay. Okay, and of course, you have the path, cost, and the depth. Okay, so for the path, cost, and the depth, I will assign 0, 3. Okay. Okay, so this is the structure of the search tree. Okay, this is the structure of the search tree. Okay, we always ask is, Professor, so why you don't add, why you actually don't include a pointing device pointing or references pointing the child to record the child node of each node in the search tree. The reasoning is that we use the search tree quite differently than binary tree. Okay, when you are storing binary tree, what you will do is you will store values in the binary tree, and then later you will do operation like data retrieval from the binary tree. Okay, but search tree is another story. Okay, the search tree is actually a data structure to help us record the path that we have been explored so far. Okay, and we at the end of the day, we don't need to keep this whole search tree. We only need to keep the route that connect the initial state to the goal state. Okay, so if you keep on searching and if you are reaching the goal state, then you are holding the node that is the goal state. Okay, and you can always keep on referencing the parent node, and you can trace a route back to the initial state. Okay, and at that point that you finish the using okay the search tree, because you have already output the solution to the problem. Okay, so in the whole usage of the search tree, we actually don't need to know the child of the nodes. So that is the reason why we don't keep it. Okay. So any questions?
I don't.
So when you are, although I am drawing the search tree in this manner, okay? Okay, for any node in the search tree, okay, if I want to know the path that the initial state need to take to reach the goals, to reach that node, as long as I know as long as the node in the parent know as long as the node in the search tree know their parents, okay, then the node can the path can always be recreated. Okay, so let's consider this. If I am holding the oldest node here, okay, and I know the parent of the oldest is Cebu, and the Cebu knows the parent is Eric. Okay, so as oldest, I can always reconstruct a path go back to Eric. Okay, and similar to other nodes. Okay, okay, so this is already enough to serve the purpose of keeping track of of the nodes of the path. Okay, we have another data structure that keep track on the node at the bottom at the terminal that is not explored yet. So that will be enough.
So you mean like the code on the right hand side is like you trace it from the
Yeah.
here?
Yeah.
Like this.
Yeah.
But the thing is, what we need, like our objective is to find the best way to go to here. Then wouldn't we should run from
We are doing it in an exhaustive manner. Okay, essentially we are generating all the possible pathway from the initial state. So in the process, when we reach the goal state, then we stop and we can trace back. Then that's it.
Also, instead of manually mapping everything, we ask the computer to, okay,
Yeah.
let's map it for me and then trace it back.
Yeah. Just output all the solutions. When we reach the goal state, we
We
stop. We
stop.
trace back, solve.
Okay.
Okay. So that is another issue that many students may feel difficult to understand about these algorithms. Okay, because it is not operating like how humans work. Okay, human brain will work like I know that path doesn't work, then I will not choose the path. Okay, or in human, okay, a human way of thinking is that you would actually be thinking what route would not work, and then you eliminate doing the search. Okay, but computer is actually doing the search here in a exhaustive and mechanical manner. It just output, it just keep on generating the search tree, and when the generation reaches the goal state that I stop, using the goal state and keep referring back to the parent node, I can always trace back to the initial state and I get the solution. Okay. So I understand this approach is not intuitive. Okay. This is how computer works. Okay. Computer is not operating in the same manner as human mind. Okay. So for computers, mechanically generating all the solutions and then when it reach the goal state, then it stop and trace back is more efficient and more simple and more elegant. Okay. So any questions? Still easy to understand, still following the one. Okay. So this is how essentially it works. Okay. You may think that, Professor, so if I do not keep track of the child, so how I can know what node is the terminal state? Is the terminal node, okay, is the leaf node. But that is not our concern because we have a dedicated data structure to record what node is being the new unexplored node. Okay. We in all the leaf node here, okay, we have a data structure to keep track what node is the leaf node. When we pick a pick a leaf node in the search tree for exploration, okay, that node is removed from the data structure. Okay.
Remove.
Yeah, remove from the data structure from that data structure. Okay. So when we are doing the searching, we have two separate data structures. One data structure is keeping track what node is the leaf node and not being explored yet.
So this is the unexplored one. This is what we explore.
Yes.
Then we'll just unexplore and then okay, explore, and then until it's gone.
Yeah. Yeah.
Or you think.
Yeah. So that is essentially how it works. Okay. So I understand that this is a little bit confusing and a little bit overwhelming to understand. Okay, but this is essentially how the search generally works. Okay. Any questions? Anyone at the back? Are you still able to follow? Okay. So this is essentially how it works. Okay. I understand that it is a little bit overwhelming, but you need to. I believe that when you have been learning programming for a long time, you must know that writing program and solving a problem with the computer substantial is different from how we solve problem with our human mind. Okay, and this is what one examples right here. Okay, okay. And for this part, I've already explained this is that for any node here, okay, we can always trace a path back to the root node, okay, because for each node here we record the parent node, so we keep on referring to the parent node, and then we can go back to the initial state. Okay. Okay. So I've even written a code to illustrate this. Okay. If you go to the coding part, to the sample code, you can actually see this is what we do. Okay. We just write a while loop, and then we keep on checking the curve. And then we created a variable called the node IDX to keep track of the node that we are working on right now. And each time we take the parent out and to check if it's null value. Okay, if it's not null, if it's not a non-value, then we update the node IDX to the current node IDX parent. Okay, so we do a loop and gradually trace the node from the leaf node back to the root node. Okay, we just keep on taking a look on the parent node, and for the loop indexes or loop variable, we keep updating it to the parent node. Okay, okay, okay. So this is the way we do things. If you want to trace, if you want to do a trace, okay, back trace of the path, so we start off with a leaf node, okay, and then you assign the leaf node object reference to the node IDX, okay, and you do a while loop, okay, and each time you check the node current node IDX parent node is null or not. If the node parent node is not null, that means that you still haven't reached the root node. So you can update the node IDX with the node IDX parent node. Okay, so you essentially move one step apart to the root node. Okay, you keep on doing this until you reach the root node. Then you fully trace the node, trace the path from the leaf node to the root node. Okay, okay. So any questions? Any questions? So this is a simple enough loop for every one of you, right? Okay. So this is substantially how it works. Okay. Any questions? Any questions? So I don't just write it in the lecture notes. I actually have the real code that you can refer to, such that you can understand how it really works. Okay. Okay. So any questions? So any questions? If no, then let's continue. Okay. And I already explained the actions. Okay, so for the action, okay, you want to keep track. You want to keep track what actions that lead to the agent move to a particular state, because at that time you can reconstruct the action list when you are tracing back. Okay. And also for the depth, when you are trying to add node, okay, when you are trying to add node to the search tree, each time you increment it by 1. Okay, as you can see in this diagram. And and when you are trying to keep the track on the path cost, you take the path cost of the current node or of the parent node, and then you add the step cost, and then the total would be the path cost of the node right now. Okay, so for example, the Cebu is having the path cost 140. Okay, 140. Okay, and the cost from Cebu to Fagres is 99. So you take 140 plus 99, then 239 would become the path cost of Fagres. Okay? Okay, so any questions? So any questions? Any questions? Any questions? It seems to be still you're still able to keep up, right? Okay. And let's take a look on the actual coding part, okay? So we are essentially growing the search tree when we are doing the search. Okay, so the upper part is the general tree search algorithm. In the lower part is the function that we do to expand the search tree. Okay, so essentially, what if you take a look on the search tree? So you'll see a thing called the fringe. Okay, the fringe is the data structure that keep track of the node not being explored yet. Okay, and in our case, in our scenario, the node that has not been explored first, that has not been explored yet, is the leaf node. Okay, let's consider this. If we do an exploration, okay, if we do an exploration of the search tree, then essentially we will be adding nodes right below right below the node, and that node no longer becomes the leaf node. Okay, so you can consider the fringe as a data structure that keep track of what node is in the leaf node or the search tree. Okay. Okay. And even if we are talking about the leaf node of a tree, some node have a depth that is smaller, and some nodes will have a depth that is higher. Okay, so choosing what node to explore first is the responsibility of the fringe. Okay, so if you take a look on the general tree search algorithm, the fringe will be keep tracking on the node that have not been explored, that is the leaf node. But the what node is being taken up for exploration in this part, okay, is the responsibility of the fringe. Okay, so that is the reason why the depth first search and the breadth first search will have two different data structures at the back end. One is stack and one is queue. The reason is simple. Okay, if we are using a data structure to control what node is being not explored yet, and we control which unexplored node should be explored first. Okay, so we are using the last in first out or first in first out properties of the stack and the queue. Okay, the first stack is last in first out and queue is first in first out. Okay, so we are using the properties of the stack and the queue to control what node should be explored first and what node should be explored later. Okay. So this is about the fringe. Okay. So you can see the general tree search algorithm is very simple. Each time we first insert the initial state as the first node in the fringe. Okay. Then it will keep on checking the fringe to see if there is an explored node. And if there is an explored node, okay, then we pick up the first, then we take a element from the fringe, okay, and then we check the node to see if it is goal state, okay. If it is not goal state, then we do the exploration, okay. Then we do the exploration, okay, and we do the exploration by expanding the node, okay, and then the new node will be added to the fringe, okay. And in this process, okay, because when we pick a node for exploration in the fringe, okay, we also remove that element from the fringe, okay. So the fringe is keeping in a situation that all the node in the fringe is unexplored. If you explore a node, that node is already removed from the fringe. Okay, we keep the fringe only storing the node that has not been explored yet. Okay, and in that situation, that also happens to be the leaf node of the search tree. Okay, this is by design. Okay, okay. So any questions? So any questions? So any questions? And let's take a look on the expand. Okay, let's take a look on the expand. So when we are doing the expand, so this is the thing that we will do. Okay, so we will call the successor function. So essentially what we'll do is we'll call the successor function. The successor function will actually return the neighboring state of the current state. Okay. Essentially, a node in the search tree is representing a state. Then we take the state from the node. Okay. We take the state from the node. Okay. And we use this argument to call the successor function of the problem. Okay. Okay. So the problem successor function will output the neighboring state of the state we are working with.
You mean the children?
Yeah, the children.
Oh,
So this is also the reason why, okay, the search algorithm doesn't need to know exactly how the problem works. Okay. All the things are encapsulated by the function problem successor function. Okay. All the things are already encapsulated by the problem successor function. Okay. So the algorithm doesn't need to know exactly what is your problem nature. Okay. As long as your problem is implemented in a way that the successor function can always generate the correct set of the next state, okay, the neighboring state, okay, then it doesn't matter for the search tree algorithm. Okay. So up to now, any questions? Up to now, any questions? Any questions? Any questions? Any questions? Any questions? Any questions? So that is the reason why the scramble tree search algorithm can isolate itself from the problem being solved in the first place. Because the successor function, because all the technical details of the problem itself is embedded in the successor function, and it is something that the search algorithm doesn't need to touch upon. Okay, we isolated the technical details of solving the problem itself from the algorithms. Okay, no matter what kind of problem we're working on, we still call the problem stop successor function to generate the neighboring state of the current state. Okay, so this is the beauty of this approach. Okay, and as a result, we'll generate a list of action and result pair. Okay, and if you learn Python, you will know that I can actually simultaneously assign two loop variables in this format. Okay, I assign the action and assign the result in this format. Okay, so the action here is referring to the action that the agent need to take to go to the neighboring state, and the result is the neighboring state. Okay. And then the rest of the coding here is to generate a node, a node in the search tree that represent the neighboring state. Okay. So we store the action to the neighboring state, to the new search node, and we store the neighboring states to the new search node. Okay. And then we calculate the path cost by referring to the previous node step cost plus the step cost plus the step cost that go from the current state to the new state. Okay. And then we add these two values up, and then we put it into the new state, new node path cost. Okay. So essentially this line is doing what this figure is trying to do. Okay. Essentially the path cost calculation is doing what this diagram is showing to you. Okay. And then we increment the depth by 1. Okay. And this is essentially doing the same as what this diagram is trying to do. Okay. And then because the node we are generate in this stage haven't been explored yet. Okay. These nodes are new to the search tree and they are not explored yet. So we add them into the fridge. Okay, so we add them to the successors, and the successors is returned. Okay, so as you can see here, we add the new state to the successor, and the successor is being returned, okay? And if you take a look, if you take a look to the code right here, okay, you can see a for loop right here. The for loop is taking the result of the expand. The result of the expand is actually the successor, that is the new state added to the search tree. And this new node not being explored yet and is new to the search tree is now added to the fringe in the general tree search algorithm looping part. Okay, okay. So the action is separated in two functions. Okay, we do exploration on the new or on the node that we are doing exploration on, and all this node that is newly generated as the neighbor node is stored in the successor data structure, and this data structure is returned back to the general tree search function, and the general tree search function receives the node generated from the expand, and this node is added to the fringe. Because these nodes are new, they haven't been explored yet, so these nodes are added to the fringe. So the fringe is always keeping track of the unexplored node in the search tree. Okay? So this part finishes the whole equation.
Just a quick question, like if the expand functions like explores every thing, then where would it go? Like which line can you point it?
Yeah, this line.
For
This line for loop in expand.
in expand, then in the for loop, then
if you recall what you learned in for loop, after the in, it is a sequence of element for looping.
yeah,
Okay.
but my question is, if you run the expand, then they are explored, then how come you would put it in the tree?
Those new, when you expand a node, you will generate new node, right?
Yeah.
And those new nodes are being returned. And those new nodes being returned are added back to the fringe.
So we have generated the path, but we have not researched them, so we put it.
Yeah.
Okay.
So we generate the node, but those nodes are not registered in the fringe.
Okay.
So we do this look at the end to register the node we generated, but haven't registered back to the fringe, back to the fringe. So the last loop right here, the last loop here is to take all the nodes we generated in the expand function and we register those new nodes to the fringe. Okay. So now any unexplored node in the search tree is always being registered in the fringe. Okay, so the fringe always represent all the unexplored node in the search tree. Okay, okay, it makes sense, right? So any questions? So student at the back, do you understand what I'm saying? And anyone? Okay, any questions? Any questions? So a brief recap, okay? Essentially, the general tree search algorithm is consisting of two parts, okay? We have the search tree and we also have the fringe. The fringe is actually keeping track on what node in the search tree that haven't been explored yet, okay? Have not been explored yet, okay? Have not been explored yet, okay? And the starting point of our search is that we add the initial state to the fringe because the initial state is the first node that is not explored at the beginning, at the dawn of the search algorithm being executed. Okay. After that, we keep on checking the fringe is empty or not. If the fringe is not empty, then we pick one element, and that element is being removed from the fringe. Okay. When you pick an element, the moment you pick an element from the fringe, you are going to explore it. You are going to expand it. Okay. So it is not a node that is undiscovered, unexplored yet. Okay. Because the moment you pick a node from the fringe, that node no longer become unexplored. It is now being explored. So we remove it from the fringe as well. Okay, makes sense, right? Okay, and then we check the pick up node to see if that node is the goal test, reaches the goal. If it reaches the goal, then we stop. If it is not reaching the goal, then we run the expand function. The expand function will try to do exploration on the node we have taken up, and then it will generate all the new node that the algorithm can go on exploration. Okay, and all the details are done within the expand function. Okay. When the expand function is being executed, it will keep a record. It will keep a record on the new node that should be added to the search tree. Okay, those nodes are also the unexplored nodes. Okay, okay. Because those nodes are unexplored nodes, so we do a for loop at the end of the general tree search algorithm and adding those unexplored nodes to the fringe. Okay, so that the fringe always keep a record on any unexplored nodes. Okay, so this is the whole idea of the general tree search algorithms. Okay, and if you are able to reach the goal state, then you have the node that represents the goal state. At this stage, then you can always use the traceback to generate a path that travel from the initial state to the goal state. Okay, and that will be the end of the general tree search algorithms. Okay, okay, okay. So up to now, any questions? It's still I understand that it's a little bit difficult it is too overwhelming to every one of you right here. Okay, but we can discuss this algorithm again in the next lecture. But up to now, so far, any question that you would want to raise for this algorithm? So any questions? Any question that you currently have and you want to ask? Any questions?
So where's the traceback function?
Traceback function is done after you do the general tree search algorithm. So when you done the general tree search algorithm, you get the goal state and you then run another function to do the tracing.
But is it written on the slides? No.
No, it is not written in the slides, but if you check out the coding, you can actually see I actually do it. Okay.
What?
Okay, so you can just look at the coding that I released. Okay.
Yeah.
Okay. So any questions? Any questions? Any questions? Any questions? So you can see that the fringe is actually keeping a track on all the node that is not explored. And the data structure used to be the fringe will determine what node should explore first and what node should get explored later. Okay, and that will determine the properties of the search algorithm. So that is the reason why if you take a look on the or the coding example that I show you, okay, the depth first search versus the breadth first search, they are the same. Okay, wait, where is the breadth first search? Okay, you can see that when I put it side by side, for the breadth first search and the depth first search, they are the same. Okay, the mere difference is one is stack, one is queue. Okay, in the depth first search, the stack is the queue. The stack is the fringe. Okay, and for the breadth first search, the queue is the fringe. Okay, okay. So you can see that you choosing what data structure to with the fringe will actually affect the properties of the search algorithm, and you have depth first search and breadth first search for two different types of data structure for the fringe. Okay? Okay? And that is the reason why you want to study the data structure, okay? Because choosing the right data structure, because a algorithm performance can drastically be different, even just changing what data structure you use to keep track of some records. Okay? Okay? And that is the reason why you want to study data structures and if you don't understand data structures, then you don't understand why a algorithm can behave very differently if I just use different data structure to keep record on something. Okay? So this is the end of today's lecture. Any questions? Next time we'll talk about breadth search. Okay? Okay, hopefully I can finish the discussion of breadth search and uniform call search before the new year holiday. Okay? So this is the end of today's lecture. Any questions? Any questions? For the coding part, you can always download from the Moodle, okay, and you can always refer to it to understand it better, okay. And I will end the recording now, okay, and